Hello. So let us begin with this mini composition of statistics, and from this lecture onwards, I'm going to first recall all of the things we have studied so far, and then obviously we are going to make sure that we learn more about all the topics that are to come. Okay. Now, some topics here would not need very much revisit, but I'll still do a few of them here. And what will happen is when I do a few of them, we can revisit all the special points we have visited, like the mean, the median, and then the test statistic, maximum likelihood estimators, and stuff like that. You see? So, yeah, we are gonna do some theory, we are gonna do some proper theory actually, and well, after that, I think we can straight on to go to some bakes and minimax procedures. Then we can see something about the maximum likelihood estimator and stuffs like that. Anyway, so let's get started. So, firstly, understand what is hypothesis testing. And in hypothesis testing, what we usually do is we try to understand what is the hypothesis, what is the null hypothesis. So, there are two kinds of hypothesis. The null hypothesis is written as H naught, which is this, while the alternate hypothesis is written as H1. Okay, and what we can do is we can understand this from various examples, and we can understand that this kind of problems have a lot of ways to be acceptance, but obviously first we are trying to understand how to handle this. So a null hypothesis is something which is given, and we would like to say some parts about it, some parts about the null hypothesis, where how we can handle, like let's say if the null hypothesis is theta greater than equal to 2, then the alternate hypothesis should be theta less than 2. So what happens is, if h naught belongs to the set A and h1 belongs to the set B, and if U is the universal set, then we must have A union B equals to U, while A intersection B equals to phi. This is what it should have, because the null and alternate hypotheses are basically reverses of each other, so they are complementary. Now, that being said, what we can now do is we can understand it from an example, and while also understand the various terms involved, like type 1 error, that we reject h naught when h naught is true. So type 1 error is defined as when we define type 1 error as the event that we reject h naught when h naught is true, and we can find the probability of type 1 error. Right. So it basically is this. Now, one more thing is level of significance or significance level, which is usually denoted by alpha. So we set a significance levels beforehand for our test, and we say that if okay. So well, obviously this is what we call as the type 1 error. So probability of type 1 error given theta, if it is less than equals to alpha, which is significance level, and this usually gives us that the test is significant and we should proceed with it. But if the probability is greater than that, then there are other ways to test that. Similarly, there is a type 2 error. So this is called type 2 error, and it means that we are going to accept h naught when in reality h naught is not true, which is h naught is false. So this is also a type of error, and it is called basically type 2 error, where or we can also call it bit of theta. So there are various ways of doing that. So since it is usually denoted by beta, you can write beta of theta, where theta is the parameter of the test statistic. Now, so we are given this entire thing, and now we are going to understand each and every problem in a very similar way. So what we are going to do is we are going to do three more examples, and very typical and very nice examples actually. And what happens is, when we do these examples, we are going to need a lot of basic theory, and theory that we have studied in statistics and theory that we have just studied right now, which is basically the application of these things. So I'll give you a minute to understand this on your own, and then we can start. Now for the examples part. I'll write down the questions first and then we can solve them. So consider a radar system that uses radio waves to detect aircraft. The system receives a signal and so understand the problem carefully first. Read it once again when I complete finishing it. When I finish the problem, and then after a while we can start discussing the solutions one by one because there are multiple parts to this problem as well. So up to this part we are clear because what we have said is this, and we understand what W is. W is basically a standard normal variable, a normal variable, a normal random variable with mean 0 and variance 1 by 9. Now, that brings question A. So I'll explain the problem again, but let me just write down the questions. There are five such questions. So the first one is write the null hypothesis. Write the null hypothesis and the alternate hypothesis in the terms of theta. So that completes the questions, and now let me explain how do we actually do it. So basically, it says that consider a radar system that uses radio waves to detect aircrafts. So there is a radar system that uses the radio waves and it detects aircrafts are present or not. So this how it works is the system first receives a signal, and based on the received signal, it needs to decide whether there is an aircraft present or not. Right now, if X is the received signal, and we already know that if X is W, then there is no aircraft present, and if X is 1 plus W, then there is an aircraft present. Right now, here W is just W belongs is basically a normal random variable with mean 0 and variance 1 upon 9. So that's the probability distribution of W. So W takes values according to which has probabilities according to a normal distribution with mean 0 and value variance 1 by 9. Thus, what we can do is we can write x equals to theta plus W. We're just trying to introduce a parameter, and you would notice that if theta is 0, then x is basically W, which means there is no aircraft present, and if theta is 1, it means there is an aircraft present, and we can write x is 1 and 1 plus W. Now suppose that we define the null hypothesis H naught as no aircraft is present, while the alternative hypothesis H1 as an aircraft is present. Now the questions. Let's go for number 1. Write the null hypothesis and the alternative hypothesis in terms of theta, right? So the simple hypotheses are as follows. Part A, we have that H naught, which is the null hypothesis, it can be written as theta equals to 0. That is, no aircraft is present. Then we have H1. H1 is basically the alternative hypothesis. So let me write down alternative, and this is theta equals to 1. That is, aircraft is present. Okay. Now to decide between H0 and H1, we look at the observed data, obviously, and this observed data tells us if we can differentiate between H0 and H1. That completes part 1. Let's now for B, design a level 0.05 test to decide between H0 and H1. So when we say a 0.05 test, what we actually mean is we are trying to decide, we are trying to make a test which can help us distinguish if to decide between what is true, H0 or H1, what to accept and what to reject, and the level of significance should be 0.05, which should be our helping hand. So So to decide between H1 and H0 and H1, we look at the observed data. The observed data is just the random variable x, right? The observed data random variable x under H0 x follows normal distribution with mean 0 and variance 1 by 9, and under H1 what happens, so this is under H0, right? And under H1 what happens is it follows normal distribution with mean 1 and variance 1 by 9. Why is it so? I'll explain that. Because under H0 W, therefore E of x is equals to E of W, and W is a standard normal variable with mean 0. So this is this, and also variance of x should just be variance of W, which is 1 by 9. Therefore x also follows a normal distribution with mean 0 and variance 1 by n. And under H1 x is 1 plus W, and this means E of x is simply, so the mean is 1, and adding a constant to the variable doesn't change its variance, because variance of x then would be variance of 1 plus w. Therefore x follows normal distribution with mean 1 and variance 1 by 9. So yeah, that's how it works. Now the test. Now what we are saying here is we can suggest the following test where we choose a threshold c, and if the observed value of x is less than c, we can choose h naught. Otherwise, if it is larger than c, we can choose h1. So that's what we are going to do. Now to choose that c, we are going to use our required alpha. So let's see. Probability of type 1 error is basically reject h naught given that h naught is true or given that h naught, right? This means when we reject h naught is x greater than c, right? And when h naught is true, it's basically h naught. And this means that x greater than c given h naught under h naught. So when h naught is given, it means that x follows a normal distribution with mean 0 and variance 1 by 9, right? So it only means that this is w by c, and this can be written as 1 minus phi c, where phi is the standard normal CDF, right? Actually, not phi, it's 3c, because I'll explain why. It should be like this. W has a variance of that, so we have to divide both sides by the standard deviation, which is this, and only then w by 1 by 3 is a standard normal variable, and then we can write probability of z greater than 3c. This is equals to 1 minus phi of 3c, right? Now the type 1 errors probability is usually the significance level, then alpha equals to, right? This means Therefore, C is basically 1 upon 3 phi inverse 1 minus alpha. Now, when we let alpha equals to 0.05, since alpha equals to 0.05, we have C equals to 1 by 3 phi inverse of 1 minus 0.05, and if you calculate this, what you get usually after dividing by 3 is 0.548, which is the threshold. So our test is complete. Now let's go to number C. Find the probability of type 2 error beta for the test. Okay, so we are trying to find the type 2 error now. So we have to make notes of first thing, that is so since the alternative hypothesis is simple, which means that basically when you are going to do the alternative hypothesis, we see that there is exactly one value included in it, that is theta equals to 1, which means it's a simple hypothesis, and thus the probability of type 2 error is basically accepting h naught when h1 is true, right? So when do we accept h naught? We know that we accept h naught when x is less than c, right? And given h1, but under h1 x is 1 plus w, so it can be written as 1 plus w less than c, right? Now this means the probability of w less than c minus 1, and we can write this as z less than 3 into c minus 1, where z is a standard normal variable, and this amounts again to the CDF 3 of c minus 1. And now since c is 0.548, we have beta equals to 0. Not 588, it's basically 088, which completes our part B, right? So for part D, we see if we observe x equals to 0.6, is there enough evidence to reject h naught at the level 0.01? Okay, let's do that. Since we have already obtained this previously, we can use right, but here x equals to 0.6, which is less than c. Thus, we cannot we cannot reject h naught at alpha equals to 0.01 if x equals to 0.6. So there is not enough evidence to reject that. Okay. Now we come to the last part, which is part E. If we would like the probability of the missing an aircraft to be less than 5.1, right? Less than what? Less than 5%. Sorry. Yeah. What is the smallest significance level we can achieve? Okay. So now what we want is we want beta equals to 0.05, right? Then and this gives you 0.452, right? Thus what we understand is we need to have c is less than or equals to 0.452 to obtain this. Now we see that the smallest significance level we can achieve with this is, and now since significance level is the same as type 1 error, we can see this is equals to phi of 3c, and this is less than equals to 1 minus phi of 3 times 0.452, which equals 0.0875. So the smallest value is 0.0875, and that would complete this one. And the prerequisite will also be added with the videos about obviously about the normal CDF, standard normal CDF, and then we would have something about integrations as well, and we'll do more examples again. In statistics, we deal about something called data. When I say data, what I mean is we have clusters of points which represents some identity or some information about a certain quantity, and we would like to investigate about those data points or those cluster of points, and we would like to find certain information about it. For example, what we can do is we can measure heights of certain people. So let's say we have 10 people, and what we do is we measure heights for each of them. What we can do is we can name the heights measured as x1, x2, and all the way up to x10. Let this be the data points. Okay, so what are these? These are the data for our sample experiment or whatever we're going to do. Now using this data, what we can do is entirely a different subject, because there are a lot of things we can try on this data, but for the basics, for the sake of basic statistics, what we can do is we can find the mean, the mode, the median, we can find the skewness, the kurtosis. Also we can see if they fit into any probability distribution, and moreover what we can do is we can find probabilities of certain heights being improbable or certain heights being like very likely. right? And maybe there are more than 10 people, maybe there are like 1,000 people, and we did a random sampling of those 1,000 people, and we selected 10 people at random, and then we selected the heights. And from this heights, what we need to do is we need to give a general idea about what would happen to the heights of the other people, or you can say the height of the population, which is of the 1,000 people. Can we get an idea about the height of the population from the height from the data points secured in this sample? That is the ultimate question. That is, let us say we were trying to investigate some statistics about the whole country, and you know there are a lot of people in the country, right? So let's say there are 100 crore people right now, for example. And what we want to do, we cannot sample 100 crore people, that would take a lot of time, and that is why we are being realistic here. We are not really being mathematical, because in mathematics we can even sample 10 to the power 100 people, right, with in a finite number of years. But that doesn't make sense. So let us say we can sample 1 lakh people or 100,000 people, and we would like to get an idea about the whole population from the sample of this 100 lakh people, 100,000 people. And what we would like to do is we would like to select them randomly and uniformly from the population, so that no selection is biased. Every selection is uniform, and every selection is equally likely. When we do that, the question is, can we get the idea about the whole population? Ideas like, what is the average height of the population? Ideas like, what is the height that goes on the furthest? Above which range do we have a 20% chance of getting a certain height, and stuff like that, you know. So we shall begin with something called mean. So what is the mean? Let me write it down. Right. Similarly, the median. So if this is the mean, the median is given by and after we are done sorting the data in ascending order, what we need to see is the middle points. Now, since there are an even number of them, there are two middle points, that is x5 and x6, and they contribute to the median m, which is given by the average of this two. Okay, and if it were not the if it not were even, let us say we had 5 quantities, then there is only one middle number, that is the third one, so we only take that one, right? So it makes sense, because what we understand from this kind of criteria is that we need to be clinical about our data set, and there are a lot of things we can do with the data, and it's usually a good idea to sort them into ascending order before doing any calculations, because it helps us figure out how the data is increasing. We can also graph the data. So these things, this mean, this median, whatever we're talking about, these are called statistics. So statistics are basically a function of the data points. So An example of a statistics would be, so covariance of x comma y would be e of xy minus e of x into e of y, right? Where e of y is defined as integral over all r y into f of y dy, and e of xy on the other hand is basically a double integral where fxy x comma y is the joint distribution of x and y. So this provides the way to make sure that we have our expectations correct, and obviously integration is very much required in each of probability and statistics courses, because integration and derivative, they form the base of calculus, and in each step we shall find ourselves to be doing some kind of integration or differentiation, right? So that is one way. Now let us see what we can do with some of the things we have here. Let us begin with a topic here. So what is point estimation again? So we have talked about it before in probability, but let us talk about it in detail here. What is point estimation? Suppose we have B, a point estimator, for a parameter theta. Now what we do know is bias of a estimator is as follows. So bias of an estimator is given by expected value of the estimator minus the estimator. You see? So that is how bias is defined. And we call it unbiased if bias is 0. So we call so if this happens, we call our estimator unbiased, right? Now we can take an example to see that why this is the case and how we can prove such questions. So let us take a small example. So that is the question in we need to show, not of itself, obviously it's unbiased estimator of theta equals to exi. The parameter is theta, which is equals to e of xi for every I, right? So how do we show that? We see that e of this phi cap is basically e so now we use the properties of expectation as follows. Therefore, we see that e of phi cap is basically equals to theta, which means it's a phi cap is an unbiased estimator of theta, and that is why it is basically unbiased, and the problem is solved. Now, this is how we solve this problems, and showing that something is an unbiased estimator specifically involves finding the expectation of the point estimator, and this expectation may well involved some kind of integration or summation, which we have discussed before, I think, and those are required. Now, after this, what we will learn is the mean squared error. So this is the mean squared error, because phi cap minus theta is the error that we make when we are going to estimate theta based on phi cap, because see, phi cap is an estimator of theta, right? But since we say estimator, we are not really guaranteed that phi cap would always equal to theta, so it estimates theta, so there can be some error, and that error is given by phi cap minus theta. And mean squared error is basically we square the error first, which is phi cap minus theta squared, and then we take the mean of it. And in statistics and probability, when we say mean, we always mean the expected value, because the parameters and everything else, they can be a continuous random variable or a discrete random variable kind of thing, and we need to do integration or summation over that, right? So that is one way. Also, what we can find out from this is So the MSE is basically the equal to variance of the estimator plus bias of the estimator squared. This is another way to find out that. Now, here comes an important property of showing something is a consistent estimator. So our topic is how to show how to show if some estimator is consistent, right? To do that, what we can do is we say minus theta is greater than equal to epsilon, and this is equals to 0, of course, for all epsilon greater than 0. So this is basically the definition for the epsilon delta case and stuff like that, and we can make sure that this works. So let us do one example for that. Suppose x1 x2 all the way up to xn be a random sample with mean e of xi equals to theta and variance of xi equals to sigma square. Okay, we need to show that is an consistent estimator of theta. And obviously we first do the integral definitions of this. We want to say that this is, since let fxx be the common PDF, then exi is simply fx dx, while variance of xi is x minus exi squared fxx dx. Okay, and we want to show that theta n is a consistent estimator, where theta n is basically equals to the sample mean. So given and we would like to show that this is the consistent estimator of exi, and let exi be equals to theta, which is also given. So therefore we need to show the following. So then probability that theta n cap minus theta absolute value is greater than equal to epsilon is equal to, so what we do see here is that they have a common PDF and they would like to, they can be treated as equals, right? Now this means that what we can do is we can use the Chebyshev's inequality here, because we see that E of theta n cap is E of 1 by n summation of I equals to 1 to n xi, which is 1 by n and this becomes theta, right? Therefore using Chebyshev's inequality we have less than equals to variance of theta n by epsilon square, and now variance of theta n is basically variance of x bar by epsilon square. Now what is variance of x bar? Variance of x bar is simply equal to and this would be 1 by n square variance of summation from I equals to 1 to n xi, and this would be n into sigma square, so it becomes sigma square by n, right? Therefore probability that theta n cap minus theta is greater than equal to epsilon is less than equals to sigma square by n epsilon squared. Therefore limit n tends to infinity, probability that theta n cap minus theta is greater than equal to epsilon is less than equals to 0, and this means that obviously since probability can always be is always greater than equal to 0 as well, therefore limit zero. So theta n is an estimator of theta, and this is proved. Limit n tends to infinity, probability of theta n cap minus theta. Theta is the parameter which theta n cap is estimating, of course, greater than equal to epsilon is equals to 0. So we say that theta n is a consistent estimator if the following property is satisfied, right? Now obviously we also defined that MSE of theta was simply equals to expectation of theta n minus theta, actually theta n's MSE squared, right? Then we see that if limit n tends to infinity MSE of theta n equals to 0, then theta n is consistent. This is another property. We can prove it as follows. We see that and this thing here, right here, we can obviously understand that this is less than or equals to the variance and bias, right? So what we can do is as follows. This is by Chebyshev's inequality, but the above thing is just MSE of theta n, right? And this would be 0 because we know that limit of MSE of theta n is also 0. And if that happens, theta n is again a consistent estimator. Now that being said, what we would like to do now is this maximum likelihood estimation. Now, what is a maximum likelihood estimation? Well, obviously, when we have an MLE, we also call it MLE. When we have an MLE in form, what we do is usually estimator for a random sample is given by, so this random sample is given by so this is our maximum likelihood estimator defined, and we do this like this. So we take the product of the PDFs basically, and the PDF is dependent on some parameter theta which we are estimating. So that's how we do it. So we are trying to estimate the probability or the value of theta for which the likelihood is maximum. Okay, so that is what we are going to expect here. Now, how do we evaluate this sum? Well, obviously now we turn back to our calculus days and we remember that we can take logarithm on both sides. So and taking the logarithm of this would give us right? And what we can do is we can define this one as, let's say, log of capital L, and log of capital L is equal to this, and we need to maximize log of capital L. So differentiating both sides, we have, so firstly the question asks us how do we differentiate it both sides, right? So, well, it's obviously L prime by L, and we are differentiating it with respect to theta, of course. Okay, so since we are maximizing theta, we are differentiating it with respect to theta, and differentiating, you get something like this. Comma theta. Therefore, L prime is equals to xi theta divided by fxi xi theta, and this is equal to 0. And when this is equals to 0, we can find out certain values of it. So whatever theta we get is called theta mle, which maximizes the likelihood. And we sure would see some example here, and that example would be this. The example is crucial to understanding what we are doing, because otherwise we would never know how to apply it. So the example is, suppose I'll just write down the question first. So we have observed the random sample x1 x2 all the way up to xn, and suppose we have that this xi's belongs to normal distribution of theta 1 comma theta 2, right? So what we need to do here is we need to find out the estimators for theta 1 and theta 2, and we also need to find out the maximum likelihood examples. Okay, so what we need to do here is obviously the PDF for all the xi's given the two estimators theta 1 and theta 2, or the two parameters, is given by 1 by root over 2 pi theta 2 e to the power minus xi minus theta 1 squared by 2 theta 2. Now let us find out the actual value, and let us see how do we do it. So the likelihood function, to find the likelihood function, we see this is the expression, right? And with this expression we see that we can write this as product of I equals to 1 to n, and this L is basically the likelihood function which we will be defining now, and well in the upcoming examples as well we are going to use the same likelihood function for x1 up to xn, and it doesn't matter how many parameters are there, we can estimate them all. So this gives us this would be, since the 1 by root over 2 pi theta 2 is a constant independent of I, we see this is equals to 2 pi theta 2 to the power minus n by 2, and the exponentials are all the product of two exponentials simply adds up the argument, so it's basically exponential of this, right? Now therefore taking the logarithm on both sides, ln of L should be equals to minus n by 2 ln of 2 pi theta 2, not a plus actually because we have exponential of minus, so exponential and logarithm are inverse functions, so log of exponential is just whatever is the argument, so minus right. Now to find out the expressions and the maximum likelihood expressions for theta 1 and theta 2, we need to do them one by one. So let us start with theta 1. Starting with theta 1 we have, and obviously all the derivative formulas and stuff and integration would be required here, so that would be embedded with this video for your forsake needs. This would be 0, while this would be 2 times therefore this gives us L prime by L equals to minus 2 I equals to 1 to n xi minus theta 1 by 2 theta 2, right? And setting L prime equals to 0, we have we see that summation of I equals to 1 to n xi minus theta 1 is equals to 0. This means that n theta 1 is equals to I equals to 1 to n xi, or theta 1 is just 1 by n I equals to 1 to n xi. Therefore, the MLE has been found, and it is 1 by n summation of I equals to 1 to n xi, which is just the sample mean. Now let us do the same method for part 2. Now the first term was minus n by 2 log of 2 pi theta 2. This one would be useful here, and thus we have minus n by 2. Differentiation of log of 2 pi theta 2 is basically 2 pi theta 2 2 pi, and this one, the only term here is 1 minus 1 by 2 theta 2, which would be basically minus 1 by theta's differentiation is 1 by 2 theta square. So this term 1 by 2 theta 2, so this minus 1 by theta 2 will only be differentiated, right? And this is theta 2 to the power minus 1, and when differentiated this will become minus 1 to the power theta 2, so basically it's 1 by theta squared. So this would be plus 1 by 2 theta 2 squared I equals to 1 to n xi minus theta 1 whole squared, because this term acts as a constant, right? And therefore L prime by L is minus n by 2 theta 2 plus 1 by 2 theta 2 squared I equals to 1 to n xi minus theta 1 squared. Setting L prime equals to 0, we have therefore and this is just sigma square, right? Therefore we see that theta 1 MLE is just x bar, while theta 2's MLE is sigma squared. And this is how the likelihood is calculated. Until now it was MLE, it was point estimation, so these are the things we have done, and we would like to do some more. Now what happens is, once we try to get hang of this test statistics and this stuffs like this, what we actually want is to understand the ideas behind these topics, right? So in statistics what happens is, when you have a data set and you're trying to manipulate with it, you're trying to get some information about how the data set acts, how it works, or you maybe graph it. So let us say you have a data set x1 x2, let me write it down. We have a data set x1 up to xn. Now in this data set, what we can do is we can see that x1, x2 up to xn is a data set, and the properties described by this data set could be as follows. The mean is written like this with the x bar. It is called the sample mean because we believe that this data set x1 up to xn, if it is not the population, then it was taken from the population by some sampling method. Now there are a lot of sampling methods in existence: uniform sampling, random sampling, and then there is collective sampling and lots of others of them. Okay, cluster sampling. So a lot of types of sampling are there, and they were taken by any one of those methods or a completely new one maybe. But anyway, they are members of the population and they represent a sample of the population, right? Our target is to understand the features of the population given this sample. So firstly, the sample mean is this. Okay, this is the sample mean, and we also know the variance is let me first I have already defined you moments, but I'll just write it down again. The average, which is given like this average e of x, or the expectation of the data set, if the data set is continuous, maybe discrete here in this case, then it is basically equals to the sample mean, right? And this sample mean is the best estimator for the population mean. So if the population mean is mu, this means that expected value of x bar is simply equals to mu. Okay, now there are a few other things we should note, that we have studied this kind of things, and what we would like to understand is what is a z score now. So we would like to understand z score. So how is a z score related and what is a z score? So z score comes from the z distribution. It is a standard normal distribution. So let me give you an example. Given x is a random variable following normal distribution with parameters mu and sigma square. Okay, find the z score for, okay, so we want to find the z score for some value, and we are not entirely sure how to do that, but if you are asked to find the z score for some x equals to k, then the z score for x equals to k would be k minus mu by sigma. This is the z score. So what it means is that the z score basically follows the normal distribution. Now how to find probabilities of certain things? So suppose we have to find probability of x less than equals to alpha. Okay, so if this is the case, then what we do is we see that we subtract by the mean on both sides first, then we divide by the standard deviation, Now, since x is now if x is basically directly normal variable, it's fine. But if x is just a representative of a sample which has n entries in total, then what we do is this: we multiply it by root n on both sides, and same here. Now this x minus mu by sigma multiplied by root n. Now let t equals to root n by sigma into x minus mu. We can show that t is standard normal, that is t goes from normal of 0 comma 1. So when this happens, what we see that therefore probability of x less than equals to alpha, this value would just be probability of t less than equals to root n times alpha minus mu by sigma, right? And for the standard normal variable, what the answer would just be minus infinity to root n of alpha minus mu by sigma 1 by root over 2 pi e to the power minus x square dx, or it can also be written as phi of root n into alpha minus mu by sigma, where this phi represents the standard normal CDF, where phi is this, right? Now the integration parts and all these things, the prerequisite for integrals would be embedded from my previous videos as well. You'll get that. But the question here remains that when phi and when we have the standard normal variable, we can easily find out, and this is essentially what we call the z-score. The values of the standard normal variable for different probabilities have already been listed out quite often, and what we can do is we can understand if this function really is required in order to understand all the different properties of any probability we ever get. And when the values are like large enough, or when the sample size is large enough, obviously, then every variable can be approximated into the standard normal variable distribution, and this is basically where the central limit theorem comes into play. So what is the CLT? Given a random sample xn, where x bar is x1 plus x2 plus xn by n, and variance of xi is sigma square less than infinity. So when you have the mean and the variance of each of them, they come from the same distribution, which are IID. Of course, I want to write IID here, and this sample mean is mu. So basically, what I want to do is E of xi is mu. Okay. So when this happens, we can write the CLT states that this. Or in other words, or what you can do is you can write like this: probability of x bar less than some t can be written as probability of z, where z is a standard normal variable, less than t minus mu by sigma square by actually sigma by root n, not sigma square. So let me correct this part. Sigma by root n. Right? And this only happens when you have limit n tends to infinity. So it basically becomes phi z of t minus mu by sigma by root n. So this is how the CLT works. So it can be for any distribution. It may be for a binomial distribution. It may be for a Poisson distribution. It wouldn't matter really, but it can be for any distribution. And the prerequisite for this variance and exponential stuff would be given at the end of the video as well. So you can check that out as well. So this is the CLT, and we will talk more about it and solve maybe after that, or maybe some problems at the end. But this is it for this one. Thank you for watching. So please download the Breatter Maths app, which is given in the description. It is a mathematical app where you can find all the necessary statistical calculators like chi-square calculator, one variable means, population means, t-value, and much more. You can also find calculus related calculators like integration, derivatives. There is a section where you can find what's coming up next. There is a section completely devoted on mathematical notes where you can find notes on probability, statistics, calculus, and many more are there to come. In those notes we have already explained all the examples, all the problems in theory, and we are just covering the video lessons and solutions of those here. You can check that out. Also, you can see the video solutions in a separate section where you can understand and give a feedback on what to expect next. You can ask for a problem, you can ask for a theory section as well. So please do check it out, and also do subscribe to Breatter Maths app and also its YouTube channel.